morning, good afternoon, good evening. This is your Professor T. Fareed Muhammad. We will be looking at Lecture 9, the Policy Gradient Methods, PhD AI 830, University of Cumberland. For the past two lectures, we have been in the world of value-based methods, DQN, and its extensions. The core idea there was to learn a Q function and drive a policy from it indirectly by taking the argmax. Today we take a fundamentally different approach. Instead of learning a value function and backing out a policy, we are going to optimize the policy directly. We parameterize the policy itself as a neural network and apply gradient descent to push it forward, or we can say to push it toward higher expected return. This shift matters more than it might seem. Value-based methods struggle with continuous action spaces, can't represent stochastic policies cleanly, and rely on an argmax operation that does not differentiate through the action selection. Policy gradient methods solve all three of those problems simultaneously. By the end of today, you will understand the policy gradient theorem, be able to implement the reinforced algorithm from scratch, and know exactly where it breaks down and what to do about this. So we have 5 topics today organized to build on each other in a specific order. We start with the conceptual motivation. Why would you want to optimize the policy directly at all? And what does that even mean mathematically? We then get precise about how to represent a policy as a neural network, which is more nuanced than it looks for continuous action spaces. From there, we define the objective function j of theta and derive its gradient using what's called the policy gradient theorem. It's the theoretical foundation of everything that follows. The second half of the lecture is entirely about reinforce, the first practical algorithm that implements this idea. We'll see how it works, drive the update rule carefully, and then confront its main weakness, catastrophically high variance in the gradient estimates. The solution to that baselines the advantage function, sets up lecture 10's actor-critic methods. So today's material is foundational for everything coming next. The policy gradient idea. Before we get into equations, let's build the right intuition into DQN. The policy is implicit. It is whatever the argmax or the Q function says to do. That works fine when actions are discrete and the space is small enough to take the max over. Imagine you are controlling a robotic arm and the action is continuous torque value between -10 and +10 Newton meters. There's no table of Q values to take an argmax over. You need a function that maps from the current joint state directly to the torque to apply, and the function is exactly what a policy gradient method learns. This discussion sets up the mathematical framework that makes directly impact on policy optimization as a possibility. The key challenge is that we need to compute the gradient of expected reward with respect to the policy parameters. but expected reward involves both the policy and the environment, and we can only observe samples of the environment. We cannot differentiate through it. The policy gradient theorem tells us how to work around this constraint elegantly using mathematical trick from statistics. Let's be precise about what distinguishes these two families of algorithms. Value-based methods, DQN being the canonical example, learn a function q of SA S comma A that estimates the expected future return from every state action pair. The policy is then inferred implicitly as the action that maximizes Q. This works beautifully in discrete action spaces because you can enumerate all actions and pick the best. It fails for continuous actions because you would need to solve an optimization problem at every step just to evaluate the policy, and it can't represent in reality policies that should be stochastic, like mixed strategy in a game. Policy gradient methods flip this around. We directly parameterize the policy as pi theta of a given S, a probability distribution over actions represented as a neural network. The policy outputs action probabilities explicitly, which means it naturally handles stochastic behavior, continuous action spaces, and multimodal action distribution. The policy pi theta of a given S is a conditional probability distribution parameterized by theta for discrete action spaces. The standard representation is a neural network that takes the state as input, produces a vector of logistics through the hidden layers, and then applies a softmax to convert those logits or logits into a valid probability distribution. All values non-negative summing to 1 at inference time. You either sample from this distribution for a stochastic policy or take the argmax for a deterministic greedy policy. For continuous action spaces, the representation changes. Instead of outputting a categorical distribution, the network outputs the mean and standard deviation for a Gaussian distribution over actions. You sample the action from that Gaussian, and the log probability of the sampled action is easy to compute analytically. For more complex action distributions, multimodal distributions for example, you can use normalizing flows or mixture density networks. The key constraint is that the distribution must be differentiable with respect to the theta, which softmax and Gaussian both satisfy. This differentiability is what allows gradient ascent to work. The objective function j of theta is the expected return over trajectories sampled from the current policy. A trajectory tau is a complete episode sequence, a 0, S0, comma A0, comma R0, comma S1, comma A1, comma R1, comma all the way to the terminal state. The probability of a trajectory p of tau given theta is the product of the policy's action probabilities along the trajectory times the environment's transition probabilities. The return r of tau is the sum of rewards along the trajectory. J of theta is the sum over all possible trajectories of their probability times their return. The policy gradient theorem states that the gradient of j of theta equals the expectation under the policy of the score function, the gradient of the log probability of the taken action multiplied by the action value function q pi of s comma a. This is a remarkable result because it gives us a formula for the gradient of expected return that we can estimate purely from samples without needing to know or differentiate through the environment dynamics. The fundamental insight is that even though we can't differentiate through the reward function or the environment, we can differentiate through our own policy. The reward arrives as a scalar signal. After the fact, it does not have a gradient we can backpropagate, but the log probability of the action we took, log pi theta of a given s, is a fully differentiable function of theta. The policy gradient theorem tells us we can use this as a surrogate gradient scaled the return. Reinforce, introduced by Ronald Williams in 1992, is the simplest practical implementation of the policy gradient theorem. It uses full Monte Carlo episodes to estimate the action value function. Instead of learning q pi, this with a separate network, it simply observes the actual return gt from each time step t to the end of the episode and uses that as the estimate. This is unbiased. The expected value of gt is exactly q pi of st comma at, but it comes with serious cost invariance that we'll discuss in detail. So the core idea of reinforce is intuitive. If an episode went well, increase the probability of every action you took during it. If an episode went badly, decrease those probabilities over many episodes. Actions that consistently lead to higher returns become more probable, and actions that lead to poor outcomes become less probable. The policy gradually shifts toward a sequence of actions that maximize cumulative reward. Let's walk through the update rule carefully. Theta gets updated by alpha times the gradient of log pi theta of a t given st times gt. Each of the three components plays a distinct role. Alpha is the learning rate. It controls the step size and must be tuned carefully. Too large and the policy oscillates or collapses to a degenerate distribution. Too small and learning is impractically slow. The return gt is the discounted sum of all rewards from time step t to the end of the episode. Written out explicitly, gt equals rt plus gamma times rt plus 1 plus gamma squared times rt plus 2. Continuing to the terminal state, the gamma is the discount factor, a scalar between 0 and 1. The discount factor serves two purposes. Mathematically, it ensures the return sum coverages for infinite horizon tasks without discounting rewards infinitely far in the future would contribute equally to GT, and the sum might diverge. Practically, discounting encodes a preference for sooner rewards over later ones. The reward received now is worth more than the same reward received 10 steps later. The cleanest way to think about reinforce is as reward weighted supervised learning. In standard supervised learning, you would have a data set of states and target actions, and you could train the policy to produce those actions reinforced does something analogous. It treats the actions actually taken as pseudo labels and weights the learning signal by the return they led to. Actions that generated high return get strongly reinforced. Actions that generated low or negative returns get surpassed. Three cases are worth internalizing. If GT is large and positive and gradient update strongly increases by theta of a t given st, the policy becomes more likely to take the actions from that state. If GT is negative, which happens in an environment where reward can be negative, like penalties, the update decreases the action probability. If GT is near zero, the gradient update is near zero, and the policy barely changes. The last case is that exactly the sparse reward problem. In environments where the agent almost never receives any reward, GT is near zero, almost always the gradients are near zero, and the policy never improves. This is why sparse rewards are so painful, specifically for reinforce. Reinforced use of Monte Carlo returns has a critical practical implication. Let me repeat this. This is very important for you to learn. Reinforces use of Monte Carlo returns has a critical practical implication. The entire episode must complete before any gradient update can be computed. GT requires all the rewards from time step t to the end of the episode, so you can update the policy mid-episode. This makes reinforce unsuitable for continuing tasks that don't have natural episode boundaries, and severely limits its applicability to long horizon problems where episode might take thousands of steps to complete. Variance is the central practical obstacle to making reinforced work. The gradient estimator takes GT, the return from a specific time step in a specific episode, and scales the log probability gradient by it. But GT mixes two things that are very different: the signal, which is information about whether action AT was genuinely good or bad, and the noise, which is cumulative effect of every random transition and action that happened after AT. Both contribute to GT equally, and the estimator has no way to separate them. The baseline trick is the single most impactful improvement you can make to reinforce, and it's elegant because it reduces variance without introducing any bias. Instead of weighting the score function gradient GT directly, we weight it by GT minus B of ST, where B is the function of the current state. The baseline subtracted quantity acts as centered reduced noise estimate of the action value. Let's make a zero bias proof concrete. For any state S, the expectation over actions of the score function is zero. This is a fundamental identity that holds for any valid probability distribution. The expected value of the gradient of log pi theta of a given S over actions sampled from pi is identically zero. Therefore, the expected value of the score function times B of S is B of S times 0, which is 0. For any B of S, subtracting B from GT changes the variance of the estimator, but not its mean. It's bias free by construction. The updated reinforce rule with a baseline reads theta gets updated by alpha times the gradient of log pi theta of a given st times gt minus b of st. We write the advantage estimate delta t as gt minus v phi of st, where v phi is a learned value network with its own parameters phi. This gives us a full algorithm with two networks, a policy network and a value network trained simultaneously. In implementation terms, you run an episode compute the GT values by working backward through the rewards. Evaluate V phi of ST for every state visited. Compute delta T at each step and then update the policy network by gradient ascent using delta T as the weight on the score function. The value network is updated separately by minimizing the mean squared error between V phi of ST. So the value network is updated separately. Let me rephrase this entirely for you again so you understand what it means. In implementation terms, you run an episode compute of GT values by working backward toward through the reward, evaluate V phi of ST for every state visited, compute delta T at each step, and then update the policy network by gradient ascent using delta T as a weight on the score function. The value network is updated separately by minimizing the mean squared error between V phi of ST and observed GT. It is just supervised regression on the observed returns. The two updates can be interleaved or done in separate passes over the episode data. Typical results show a tenfold or greater reduction in gradient variance compared to vanilla reinforce at the cost of maintaining and training the second network. Let's walk through the complete training loop step by step. Step 1, sample a full episode by rolling out the current policy pi theta. Starting from initial state, at each step you sample any action from pi theta of dot given st. Take the action in the environment, observe the reward, the next state, and continue until the terminal state. This gives you a trajectory of states, actions, rewards. Step 2, compute the returns by working backwards through the trajectory gt equals rt. gt equals rt plus gamma times gt plus 1. This backward pass is efficient and gives you all GT values in one sweep. All right, reinforce has three limitations or three interconnected limitations that motivate everything that comes next. So I would strongly suggest you to look at high variance, slow and sample inefficient, slow and sample inefficient, and what comes next is actor critique. We'll discuss that in quite details. 6 things to take away from today. First, policy gradient methods directly optimize the policy pi theta by gradient ascent on expected return. And last not the least is the actor critic is the next. Since I have been through to reinforces unbiased, baseline fixed variance, policy gradient theorem, where variance is the enemy. So replace GFT, GT with TD boosted value estimates for online updates, and dramatically improved sample efficiency is the actor critique. We'll see you in the next lecture. Happy learning.